In the last video, we worked with the contours of multivariate normal distribution and saw how they degenerate into a line in the limit. The limiting value of the sigma matrix was singular. So, the multivariate normal PDF became undefined in the limit. Now, we had used PDF for defining multivariate normal distribution. So, according to that definition, this limiting case is not a multivariate normal distribution. This is disconcerting. It is somewhat like working with rational numbers alone. They suffice for most of our usual needs, but they suffer from one problem. If you take limits of rational numbers, you may get something which is not rational. This does not pose much of a problem in our day-to-day lives, but it does make theoretical manipulations difficult. That's why we include all possible limits of rationals into our consideration and real numbers are born. Well, that's what we are going to do here as well. We are going to broaden the definition of multivariate normal distribution, which will allow the limiting cases to be included as well. First, let's see a motivating example. Again, we start with sigma equal to the identity matrix. We already know that the PDF in this case is like a bell-shaped dome. The contours here are like concentric circles, which are shown like this. Now, we start reducing this entry to 0. The contours then degenerate into horizontal lines along the x-axis. And as expected, sigma has now become singular, so the PDF is undefined. But is it really difficult to describe this limiting distribution? Not at all. Let's take a look at what has happened to the surface. Well, we are now looking at the thing vertically downwards. Let's turn it so that we may see the shape. Aha! The bell-shaped dome has flattened itself into a bell-shaped curve. Here is how we may describe the distribution. Here x is just the univariate normal random variable and y, the thin thing, is just constant. In this example, the line was horizontal. Had the points all been along a 45-degree line, then we can say that x minus y is a constant and x plus y along the line is a normal random variable. Notice that these are both linear combinations. If the line has some different slope, then the coefficients of x and y would just change. These descriptions do not mention any PDF at all, but work completely in terms of linear combinations and univariate normal distributions. This motivates the broader definition that we are about to learn. First, we broaden the definition of univariate normal distribution a little. We say that x follows normal mu 0 if x is constant at mu. Now for the multivariate case. Let mu be in RP. Let that be any vector, and let sigma be any P cross P NND matrix. Notice that we have replaced PD by NND. That is, we are allowing sigma to be singular. We shall say that a p-dimensional random vector x has multivariate normal distribution p-dimensional parameters mu and sigma if for any L in RP, any fixed constant vector in Rp, L prime x has a univariate normal distribution with mean L prime mu and variance L prime sigma L. This definition is not only more general than the PDF definition, but also much easier to work with than the PDF definition. For example, it is easy to see that if x is np mu sigma according to this definition, then expected value of x is equal to mu and variance of x is indeed equal to that sigma. This may be proved quite easily without any integration because now we have no guarantee of a PDF, so no question of integration arises. Try to prove it, it's quite simple. If you find the technique, let me know in the comment section below.